High above the blur of weather and wandering jet streams, a small fleet of silent sentinels circles Earth. Each carries a mirror polished finer than a grain of pollen, and each stares into night with a patience no human eye can match. Euclid, launched by ESA, was built to map the faint warping of starlight, called weak gravitational lensing. Tiny stretches and squeezes in galaxy shapes that betray the presence of dark matter, like fingerprints on glass. Where ground telescopes see the sky through a restless aquarium of air, Euclid drifts in vacuum. No twinkle, no turbulence, just clean geometry written by gravity itself. Soon it will be joined by NASA's Nancy Grace Roman telescope, a wide-angle cousin to Hubble that can capture a patch of sky the size of 50 moons in a single frame. Roman's gift is time, by filming billions of galaxies over years. It will watch the universe's expansion, accelerate, or ease, charting dark energy's pulse with a cosmic stopwatch. And further out, its mirrors still cooling, JWST peers in infrared, the color of cosmic embers. Those long waves slip through dust, revealing dwarf galaxies too dim for earlier surveys. Their numbers and shapes act as a census of how dark matter clumped when the universe was young. Orbit, then, is more than altitude. It is clarity. It's an unobstructed line of sight to the universe's most delicate signatures. Hence, by lifting our eyes above the atmosphere, space telescopes turn the invisible tug of dark matter and the gentle push of dark energy into crisp, measurable patterns. Back on Earth, human ingenuity answers thin air with sheer scale. In the Chilean Andes, the Rubin Observatory rests atop Cerro Pachin, telescope so wide it could swallow a basketball court. Every 30 seconds, its 3.2 gigapixel camera captures the whole southern sky, building a nightly time-lapse that will span a decade. As galaxies drift just a hair on its sensors, software measures the minute stretching of their images, the signature of dark matter's hidden scaffolding evolving in real time. Half a world away, the square-kilometer array spreads thousands of radio dishes across desert plains. Tuned to the 21-centimeter whisper of hydrogen, it will chart intergalactic gas from the cosmic dawn onward, carving a three-dimensional map of structure formation. Think of it as a CAT scan for the universe. Slice by slice, it reveals how dark matter's gravity gathered ordinary atoms into the first stars. Even traditional optical giants have learned new tricks. Adaptive optics fires lasers into the upper atmosphere, creating artificial guide stars. Computers then bend mirror segments hundreds of times a second, erasing the jitter of air and leaving star images as sharp as those seen from orbit. Add machine learning algorithms that sift petabytes of data for lensed arcs and supernova flares, and mountaintop domes become smart sensors, not just big ones. Together, these ground titans complement their spaceborne cousins. One offers an unblinking movie, the other the color and depth of a cosmic MRI. Giant telescopes on Earth trade altitude for aperture, capturing the evolving dance of dark matter and hydrogen in unprecedented detail. On the 17th of August 2017, two neutron stars, objects so dense a teaspoon would outweigh Everest, spiraled together in the galaxy NGC 4993. LIGO and Virgo felt their final seconds as a rising whoop in spacetime, signal as unmistakable as the chime of a front doorbell. Astronomers call such events standard sirens. Like supernova standard candles, they reveal distance, but through vibration rather than light. The louder the ring, the nearer the source. And Einstein's equations set the volume precisely. Just 1.7 seconds after the gravitational wave faded, telescopes caught a flash of gamma rays, then an afterglow that blossomed from ultraviolet to radio over days. That flash supplied the missing half of the cosmic coordinate, redshift. Distance from the siren, expansion rate from the glow. Combine them, and you have a fresh measure of how fast the universe is stretching right now. Future mergers will dot that ruler across cosmic time, offering a check on supernova results and a new way to watch dark energy's grip strengthen or slacken. Standard sirens are refreshingly self-calibrating. They need no complicated models of star brightness, no assumptions about galaxy dust. The physics is locked into gravity itself. As LIGO upgrades and the coming Einstein telescope tune their ears, dozens, perhaps hundreds of these cosmic doorbells will ring each year, each one a data point on the graph of universal growth. Gravitational wave sirens let the universe announce its own distance, turning cosmic collisions into talking rulers that chart the tempo of expansion. While telescopes scan the heavens, basement laboratories wage a quieter campaign. One waged in total darkness, shielded from cosmic rays, vibration, even footsteps on a distant sidewalk. Deep inside an old South Dakota gold mine, the Lux Zeppelin detector holds 10 tons of liquid xenon as pure as melted starlight. Should a dark matter particle nudge a xenon nucleus, a faint flash, and a handful of electrons betray the encounter? Months may pass with no spark, but patience is the currency of discovery. Just meters away, another experiment listens for subtler guests. Incoherent elastic neutrino nucleus scattering. Neutrinos ricochet off whole atomic nuclei like ping-pong balls, striking bowling balls. Detecting that tiny recoil fine-tunes our grasp of the weak force and could flag new physics that mimics dark matter's messengers. Even gravity itself is placed under a microscope. Atom interferometers launch clouds of ultra-cold rubidium upward and let Earth's pull bend their quantum wavefronts. Compared to such fountains side by side, and any extra tug, a hidden fifth force linked to dark energy or exotic particles would tip the balance. Similar interferometers now fit on tabletops, their laser lattice acting as rulers a billion times finer than a human hair. And then there are quantum sensors cooled to a hair's breadth above absolute zero. Tiny superconducting loops, called squids, monitor magnetic fields a trillion times weaker than a fridge magnet, ready to flag passing axions or other dark whispers. Buried tanks of xenon, levitated atoms, and superchilled circuits turn earthly laboratories into stealth observatories. Places where the subtlest shiver could reveal the universe's hidden ingredients. Walk into any living room after sunset and you will find a quiet miracle. Laptops, tablets, and phones connected to telescopes half a world away. Through projects like Galaxy Zoo and Backyard Worlds, more than 2 million volunteers have clicked their way through deep sky images, labeling spiral arms, spotting warped rings, and flagging the telltale arcs of hidden gravitational lenses. No supercomputer, however fast, can yet match the human knack for pattern and surprise. A retiree in Manchester once found a lens the experts had missed, its ghostly smear betraying a heavy halo of dark matter 12 billion light-years distant. Yet the data flood is swelling beyond any human army. When the Vera Rubin Observatory begins its 10-year survey, it will stream 20 terabytes of sky each night, enough to fill a hard drive tower taller than a giraffe every month. Machine learning algorithms trained on the hand-labeled treasure from citizen scientists will comb that torrent in real time, flagging subtle shears in galaxy images that reveal dark matter clumps, or the tiny brightness wiggles that hint at a type Ia supernova half a universe away. In this partnership, humans provide intuition, AI provides stamina. Together they will map the hidden mass between galaxies and refine the timeline of cosmic acceleration with a precision no single telescope or single mind could achieve. From kitchen tables to neural networks, the hunt for the unseen has become a team sport where every click teaches a computer to sift the cosmos for shadows. We now possess an arsenal worthy of the mystery. Satellites that photograph space like cartographers, ground telescopes that listen to the hiss of hydrogen across epochs, wave detectors that feel the universe ring, and underground chambers that wait in breath-held silence for a single flash. Add to that the collective curiosity of millions, and the tireless focus of artificial minds, and the invisible begins to take shape. Contours traced in lensing arcs, siren chirps, and atom-scale shivers, yet knowing what is out there is only half the story. The next question is what happens next? Dark matter sculpts today's galaxies, but dark energy scripts tomorrow's sky. Will its silent push stretch space until every star slips from view? Could an unforeseen twist in its character tear atoms apart or relent, letting gravity call the cosmos homeward? In Part 6, Fates Written in Darkness, we will fast forward through billions of years. Following models that hint at heat death, Big Rip, or cosmic rebirth, we will watch the Milky Way merge into a lonely island. Weigh the prospect of dark matter decay and imagine technologies like Dyson spheres. Galaxy hopping that might let future minds thrive against the widening void. Join us as we step beyond measurement into prophecy, tracing the paths our shadow-ruled universe may yet walk. Invisible forces built the heavens we know now. They will decide how long those heavens endure.